Before we have a look into the active power components, starting out with the diode, I would like to give you a sneak preview of how a buck converter works. A buck converter has typically a DC voltage source at the input connected in series with a switch. From there on, we have a diode with the anode being connected to the negative potential of the voltage source and the cathode being connected to the switch and further on towards the output to the inductor here, and then having an output capacitor from the inductor back to the ground potential, as well as in parallel to that capacitor, the actual load of the buck converter. In this case, we model the load as a resistor, as it is very often done. Now this switch up here is ideally operating as fully closed or fully open. If we have it fully closed, we are creating a connection between the voltage source through the closed switch to the so-called switching node. The switching node is the node connecting the switch, the diode, and the inductor. From there on, current can directly flow towards the output. This node is pulled up to the input voltage. Therefore, the diode down here is in reverse polarity, is blocking, and the current is flowing through the output capacitor, charging this capacitor, as well as supplying the load with the desired current. From here, we can close the circuit going all the way back to the voltage source. Now, the other state of operation is when this switch up here is fully open. When this switch is fully open, we still have a current flowing in this inductor from the previous state. And as we have learned from the inductor video, we cannot have jumps in inductor current. So that current has to flow somewhere. On the right-hand side of the inductor, it would still provide energy to the capacitor and to the load. Now we need to close the electrical circuit. And as the path through the voltage source at the input and the switch is opened by the switch, we need to close the circuit through the diode. So the diode would be turned on by the current flowing through the inductor and is conducting from its anode to its cathode, and the circuit is closed. Let's recall what happened to the diode during those two operating states. During the operating stage, drawn in blue, where the switch was closed, the diode was in reverse bias. We had the input voltage across the diode and no current was flowing through the diode. During the red operating stage, the diode was conducting all the inductor current. Current was flowing through the diode, and ideally the diode is shorting the switch node all the way down to ground, and ideally there is no voltage across it. Now let's zoom in on this diode and have a closer look at it. First of all, we need to define the voltage and the current polarities. I am defining the anode to be the positive voltage potential across the diode and the cathode being the negative voltage potential. The current is flowing from the anode to the cathode in a positive way. This is a very common definition for the voltage and the voltages and currents across and through diodes. However, if you decide to define the voltage or the current in the other direction, this is a matter of taste. But as soon as you have defined the potentials and the direction, the potentials and the currents with their directions, you cannot change them anymore during your calculations. If you would change them in the middle of your calculations, you would actually get wrong results. So as soon as you have defined the direction of the voltage, you need to stick to it. Using this definition of the voltages and currents across the diode, we can either block voltage with the diode, as we have seen in the blue operating mode of the buck converter on the previous slide. So we operate on the negative part of the x-axis or a very specific point at this axis. During the red operation stage of the buck converter, we were operating along the positive y-axis of the VI characteristics diagram of the diode. Ideally, we would jump from one operating point straight to the other and back again without having any other interaction with the diode. And a replacement symbol for that ideal operation can be simply drawn as a switch as is visualized over here on the right side. Now, when calculating or simulating your components or circuits, the results can never be more accurate than the models you're feeding into this process. The idealized version of a diode we've just looked into is providing a starting point for getting an estimation on how circuits work. I'm trying to give you three different stages of modeling the components, as we have already looked into in the capacitor and in the inductor section. Now, within the semiconductors, the diodes and the MOSFETs, I'm calling the first version the ideal model, which we've just looked into. Then the second version is a simple model of what's going on with the semiconductors. And the third version is trying to get as close as we can based on the datasheet that we have at hand. Now, whereas an ideal diode would theoretically only operate along the x-axis in the negative direction and stick to the y-axis of the VI characteristics of that diode in the positive direction, we actually have a forward voltage drop at the operating point of the diode. When we are conducting current through the diode, we are in forward operation now. I've just chosen an arbitrary operating point here on the x-axis, and the total forward voltage drop depends on the voltage drop across the PN junction of the semiconductor. The P and the N stands for positive and negative. That's where the positive dotated and the negative dotated semiconductor materials meet. And furthermore, it consists of a resistance RD, which is mainly based on all the connections from the outside to the junction itself. That could be the leads of the component, which are the pins. Then that is all the routing inside the package, the bond wires and whatever it is to reach the actual die, and also the routing on the die until we actually reach the PN junction. The resistance of these connections are represented by the derivative of the IV characteristics, and it can be calculated by reversing that one so we actually get a resistor. So when conducting a current through a power diode, we actually get a voltage drop across the static PN junction, which we can model through a DC voltage source. And we have that extra voltage drop at the operating point across the resistances leading to the PN junction, which can be modeled by an extra resistor in series with that DC voltage source. Now, PN is a specific kind of diode, which is actually rarely used in power electronics. Most of the diodes are Schottky diodes, but the effects and the modeling are basically the same through a DC voltage source and the resistor in series. So also for modeling Schottky diodes, this is an adequate model. Now the third stage of modeling diodes, I would like to get closer to reality and have a look into the data sheet of a very specific diode. And I have chosen the one which is called the Moore 820 PBF. The PBF means plumb-free, lead-free. So the actually electrical characteristics are mainly defined by the name MUR 820. Now, having a look at a data sheet is typically also the basis for a SPICE model. And as I have chosen three different levels of modeling a diode in here, if you start to drill deeper into actual SPICE models, you would also see various different levels on how they are modeling real power diodes. You can increase the effort of modeling until it fits your expectations, but at some point, the effort of getting an even more accurate model is starting to get more than it actually takes to build prototypes and measure what's happening in the physical lab. But now let's have a look into the datasheet of this specific diode. The cover page of the diode Moore 820 PDF looks like this. It describes the most important parameters for a practical engineering task to actually choose whether this diode is adequate for the project at hand or not. One is the average forward conducting current it can withstand, which is 8 amperes in this case, and then it can block a reverse voltage of 200 volts. We'll get back to the reverse recovery time of 25 nanoseconds in a moment. The absolute maximum ratings are specified on the first page, which is a typical thing to find on most data sheets. Physically, this diode is shipping in a so-called TO220 package, which is a very common package in power electronics. It has 3 leads because it is also used for MOSFETs, where the first one, where in the case of diodes, you actually short 2 of them out because you only need 2 connections. The physical piece of semiconductor, also called the die, is inside the body of the mold and is about that size here. So the scale of the die is actually only a few millimeters by a few millimeters, whereas the whole package is about a centimeter wide and about 1.5 centimeters high. The thickness of this device is about 5 millimeters. Pin 1 is the cathode, which is physically over here, and pin 3 is the anode, which is physically the third pin over here. Now the second one is actually not even noted here because it is shorted. On the physical device, you can see the short actually over here, and in the circuit diagram, it is indicated here. The third pin for MOSFETs, but also for diodes, is also electrically shorted to the backside of the device, which is in most cases metal. Sometimes it's covered by a mold for isolation purposes, but this backside is where the die is mounted on to actually get rid of the heat and have a good heat conduction to a potentially attached heatsink surface. Also for mechanical mounting purposes, there is a 3 millimeter hole on the backside here. Now let's have a further look into page 2, where the electrical characteristics for that diode are given. This table is giving us a bigger insight into the diode and the modeling of it that we've just looked into, the simple model and the ideal model. The breakdown voltage, the maximum blocking voltage the device can withstand, is given as a minimum voltage, so you can be sure that it actually can at least block 200 volts. Whereas the forward voltage is required to be a maximum so that you know that you would never exceed that amount of voltage. Note that it is varying a lot with the temperature. The table is defined for 25 degrees, unless specified otherwise, which is, for example, here. And we can already see that we have 80 millivolts of difference between those two values. Now, this forward voltage is the one that is very often assumed to be around 0.7 volts. And as we already can see here, the 0.7 volts are rather a very rough estimation. And for power electronics, we need to look deeper into that. The dynamic recovery characteristics are also an important section, which we will get back to. Later on in the course, we will also have a look at the thermal characteristics of those packages. But for now, let's scroll down to page number 3 of this diode datasheet and have a closer look at the IV characteristics, which is exactly the same diagram that we've just drawn on the slides for the ideal diode and for the simple model of the diode. So this diagram is representing the first quadrant of the diode characteristics with the conduction current on the y-axis and the forward voltage drop on the x-axis. The zero point 0.7 volt that we are often assuming as a typical forward voltage drop of a diode are actually on this diagram. So if we have a look when we have 0.7 volts, we can see here for the given temperature of 25 degrees C, whenever we are conducting this amount of current. The y-axis is logarithmic here, so we have 500 milliamps through the diode at 25 degrees C. Now the picture is different if we go up to elevated temperatures. And it is actually realistic that the junction temperature, represented by the J here, can get ways above 100 degrees, as indicated by these two temperatures here. Now, junction means the piece of silicon that is actually inside our package. That doesn't mean that we would also see the same temperature on the outside that we actually can physically touch. Well, at these temperatures, up at 150, 175 degrees C, the amount of current that we are conducting through the diode is actually about a decade higher than the amount of current we conducted through the diode at 25 degrees C for getting the exact same voltage drop. Typically, when dealing with converters, it's actually the other way around. You have a given amount of current, then you're getting in a specific temperature from that. And from that, you can actually read out of this diagram how much voltage drop you would end up with across the diode. Now let's get back to our model of the diode and see what these values actually mean for our diode in operation in a converter. There are two different loss mechanisms in a diode that I would like to highlight in this course. One is the conduction losses, which we can derive from the values that we actually just looked into. Now, again, having our diode model as a DC voltage source over here and a resistor in series, where the DC voltage can be read from the x-axis of the IV characteristics we've just looked into. And then the resistance is the one over the derivative of the IV characteristics at the operating point. We've seen in the datasheet that this is actually a bent curve, so we need to linearize at the point that we're working on. We can end up putting those two voltages together. We end up with a total amount of forward voltage drop while we are conducting current through this diode. Now, whenever we have voltage across a component and current through it at the same time, we can multiply voltage and current, and we end up getting power. This amount of power is actually lost in a converter and transferred into heat. Specifically for a diode and the conduction losses, let's have a look at the power by going through the energy. The energy is the integral of the voltage across the device times the current through it over time. In our case, the voltage is a static voltage, a forward voltage, and the current through it is also assumed to be DC. And as we have seen from the buck converter, the diode is only conducting during parts of the time. So whenever the diode is not on, we don't need to integrate across time. So the limits of the time integral are actually given by the operation of the converter. Note, for this simple way of modeling the losses, both the forward voltage and the current are assumed to be independent of time. That's why we can put them outside the integral, and the integral simplifies to a difference of the upper minus the lower limit. Finally, we can derive the power by putting the energy that we've just derived and average it across the time period t the converter is operating with, and we end up with the conduction losses in a diode indicated by the indexes D for diode and con for conduction in the equation 43. Now, these were the static, the time independent losses of a diode. Whenever we switch the diode, we also get dynamic losses of the diode. And therefore, I would like to go back to the data sheet and have a look at another illustration in there. If we scroll down further in the data sheet, we get various other graphs and more data about what's going on in the diode. On page 5, there is a test circuit on how the reverse recovery is actually characterized for this diode. I would like to have a specific look into the waveforms concerning the reverse recovery of a diode, represented in figure 10, which is called the reverse recovery waveform, the definitions. Now, first of all, let's draw some axes into this diagram. The time axis is here, and I'll define here that the y-axis, which is representing the current through the diode, to cross the x-axis, the time axis, exactly at that point of time where the current is changing its polarity. We are specifically looking into the switching instant where we had the diode conducting, as in the buck converter example. The diode was conducting all the inductor current, which we've drawn through the red stage. But at some point, we turn off the diode, and the switch in the buck converter takes over the inductor current. That means the diode current is ramping down to 0. But we are not reaching that 0 stage immediately, but first after the reverse recovery has taken place. The reverse recovery are charges which are stored in the PN junction, or also in the semiconductor metal junction for Schottky diodes, which need to flow in the reverse direction of what the diode just conducted. So actually the current is reversing all the way to its peak reverse recovery current, and after that one, it returns back to 0. Now this diagram is indicating the linearization of that effect. We have a maximum, and we can represent the rest through a triangular, where we have two different triangulars actually, with the base of the first one being characterized by the time TA, and the other one the time TB. The total amount of reverse recovery time is the sum of those two and the whole triangle underneath the current waveform. The area underneath that curve is defined as the so-called reverse recovery charges, QRR, and can simply be calculated by the area of the triangle. Now going back to page 2 of the datasheet, we can actually find some numbers to quantify the characteristics of this triangle. The time during the reverse recovery is measured in nanoseconds. It's again highly dependent on the temperature, but also on the amount of current the diode was conducting before it actually reversed. So here are some numbers for 1 amp as well as for 8 amps. One of the parameters that actually underlines the significance of that effect is that the amount of current for the given forward currents here is rather high and can even be around half of the maximum forward current the diode can conduct, as in this example with the 4.2 amps here, and at 1.7 amps, again, highly temperature dependent effect. Now, as we have seen from the conduction losses, there are only losses if you have current and voltage at the same time. The upper diagram represents the current through the diode versus time, and is about the same diagram as we have just looked into the data sheet. with the reverse recovery time and the time TA and the time TB. Now, the reason why we have split the reverse recovery time up into an A and a B part is that the voltage across the diode is varying significantly during these two time sections. First of all the time during the diode was conducting current, its forward voltage was rather low and is represented by the forward voltage that we have been looking into during the conduction losses. So the roughly 0.7 volts, which are not 0.7 volts in reality. During the time where the current is falling from its forward current to the maximum peak of the reverse recovery current, we have a negative voltage across the diode, which is about equivalent to the forward current, just with a different sign. This does not contribute to significant losses as the voltage is rather low. But at the time where the reverse recovery has its peak, the diode actually starts blocking the full voltage that the converter is putting onto it. In the case of the buck converter that we've looked into, that means that the switch is fully on and the switch is connecting the switching node of the buck converter to the input voltage, and therefore the diode starts to reverse bias and block the whole voltage beginning from the time where the current reached the maximum reverse recovery peak, and then onwards until the diode starts conducting again. And after that, it would cycle. The diode has been conducting for a rather long time compared to the nanosecond actions that are happening during the reverse recovery event, and we start from the beginning again. Now that we have looked into what is happening during the reverse recovery, we have the basics ready to actually calculate the losses that we are getting. Your model is only as good as the assumptions you are doing, and we have already assumed that the reverse recovery waveform has a triangular shape, and we have already assumed that we can neglect the time TA due to the rather low voltage across the diode during that time, and we are left considering the time period TB, which has a significant amount of reverse voltage across the diode. Now, using the same physical principle as before, we can multiply the voltage at an instantaneous time t across a component with the current through that component at the same instantaneous time t, and integrate over the time t to actually derive the energy in that component at the instantaneous time t. Now, remembering that we only focus on the time interval called TB, we are only interested in the waveforms covered by the blue box over here. The voltage across the diode is VR, and the time dependent to the left is only the current, which stays inside the integral in this time. Furthermore, we can simplify that integral into a triangle. The area underneath that triangle, which was equivalent to the reverse recovery charges that we've looked up into the data sheet earlier, and multiplying those charges with the voltage across the diode gives us finally the energy during the switching event of the diode. We can transfer this energy into an average loss by putting it into the equation for power and averaging across the whole period time t that the converter is operating with. So note the uppercase letter T is the whole operation period of the converter, whereas the integral limits are dependent on the event, and in this case, only cover the time TB. As the period is the reciproc of the switching frequency, we can also rewrite the equation as done on the right-hand side here. Finally, we have the total amount of losses in a diode, which is just simply the sum of the conduction losses from the previous slide and the switching losses from this slide. Now, putting all these effects together and putting some numbers on it and applying it to a buck converter is the contents of this exercise. First of all, we start out having a buck converter being quantified by its operational duty cycle, here of 25%, and a switching frequency of 200 kilohertz. The average output power of the converter is defined to be 8 amps, and we are using the diode that we've just looked into the datasheet. The input voltage is 160 volts. All of these numbers fit very well with the numbers that you can extract from the datasheet. So in that sense, we are lucky in this case. In practice, for dimensioning power converters, this would rarely be the case, and you would need to interpolate the numbers or derive them from the SPICE module from a simulation to actually find out how the diode behaves at your specific operating point. Now, I've simplified this for you already, and you can already assume that you can use the numbers from the datasheet because we are operating it exactly at the point where the datasheet is giving us the numbers. The forward voltage drop across the diode is defined as 0.98 volts at one temperature and as zero point 0.9 volts at another temperature, which is read out from the IV characteristics of the diode datasheet. Now, basically, this exercise is going two paths and repeating the same calculations just for two different temperatures. So basically, I'm asking for three things. I'm asking for the conduction losses, I'm asking for the reverse recovery losses, and finally, I'm asking for the total losses of the diode. And it turns into 6 questions as we're doing it at two different temperatures. One temperature is 25 degrees C, which is often also called room temperature, and the other one is 125 degrees C, which is a realistic temperature for the converter to operate in terms of junction temperature. So that's the temperature the silicon would see. The questions for the conduction losses are shown on this slide. The reverse recovery effect at 25 degrees C is presented on this slide, again using the 0.7 amps from the datasheet as we've just looked into, and also estimating the time TB at 25 degrees C to be around 10 nanoseconds, which is about half of the whole reverse recovery time that we have up here for a forward current of 8 amps and for a reverse blocking condition of 160 volts. The same question as we've just seen for the reverse recovery at 25 is repeating here for a junction temperature of 125 degrees. And again, we read out the reverse recovery peak current to 4.2 amps, and the time TB has changed from 10 nanoseconds to now 17 nanoseconds at a temperature of 125 degrees C. So the parts C and D of the question are asking for the average switching losses at two different junction temperatures. To pass the data on to a mechanical engineer who needs to design the cooling for our converter, we need the total losses in the device, and therefore we also need to calculate those at 25 degrees C and 125 degrees C junction temperature. We will use those values later when we look into the cooling part of this course.